Welcome to the midterm demo for our senior design project. In this video, we'll be showcasing our optical interactive chessboard and presenting its development during the stages of prototyping. In this demonstration, we hope to display the base functionality of our project as it approaches the end of its design cycle. The demo process will serve as a sort of proof of concept that will allow us to identify errors and make possible improvements and adjustments as needed to create the best possible version of the design that we can. This demo will feature two parts, the first being an overall functionality demonstration of the project as it currently stands, which will then help to understand the following segment, where we will demonstrate some key engineering specifications that helped to guide the development of this project. I'll leave you to Alec and Nikolai to showcase an example of the working design, which will then be followed by each of us explaining the different subsystems that compose the project.
Okay, so here we have our final project box. This is the final housing for all of the parts. On top here, we have some of the pieces, the bases, just to show a visual representation of how this will look. We have these rings that will be glued down onto each square to contain the base that the piece will be sitting on. And then the base is housing the illumination system that contains the IR LED.
Here we have our demo for the midterm. Right now it's just on an LED test mode to show that the LED array is working because of the live demo. I'm going to display what it looks like when a piece is identified, and it shows the valid moves it can make. So let's make it so it goes to this position is where the piece will be placed. And here we have it for a filter for a queen placed on top, and it shows all the valid moves for a queen.
So in order to display the moveset onto this LED array, we have here a 4x4 common cathode configuration for the LED array. So we have these through holes that we can connect to adjacent 4x4s in order to build it out into an 8x8, and if we had more PCBs, even a 16x16. So the columns are the anodes of the LEDs, so they are active high, and in order to not burn out the LEDs, we do have resistors, and this is all controlled by shift registers. Right now we have the shift registers, the first 4 pins for red, the next set of 4 for green, the next set for blue, and then the last 4 for the rows. And then for the rows, we're using active low, so they will read high, otherwise the row we want to send a signal to will be turned to low in order to turn that row on. Then under here is the full 4x4 of the LED array, just to give you a picture. And then over here is where we will have our MCU along with our batteries. And then we will be using just a little bit of wooden blocks to get the LED array closer to the top of the board, while also being able to run all the wires for the project underneath the PCBs.
So we have the illumination system here. It would be on the base. We'd have the button here, and we'd have the battery pack in the back. We would have 2 AAA batteries. Each battery is 1.5 volts. And here we would have the circuit, the LED here, which is 940 nanometers, and has a forward current of 47 milliamps and a forward voltage of 1.28 volts with a resistor around 60 ohms. And here's the battery pack and the switch. We would need an IR card to see the light from the IR LED. Now it's on. Now it's off. So for the next part of the system, after receiving light from the illumination system in the bases, it then goes to the photodiode under each square. And for the piece identification system, I'm using a photodiode connected in a transimpedance amplifier circuit or a current to voltage converter circuit, because the output from the illumination system typically ranges from nanoamps to microamps, and then once we boost it up and convert it into voltage, then we get a nice range of values from 0 to 3.3 volts. And then to differentiate the pieces, we're using various filters that are on the bottom that will be attached to the bottom. And we're planning on getting 7 different filters to differentiate each of the pieces in the project.
As I receive the signal from the photodiode, it gets transferred along to the analog to digital converter on the Teensy. From there, that value is converted into specified ranges and into a certain value for identifying the piece. So here, from 0 to about 70, we have it just set to not available or an empty piece, no piece available on the board. And now we can take the base here, place it directly on top, and receive the value for a king. As I lift it up as well, you can see that it ranges some different values since it's reading all of it immediately, but using a calibration system where it just waits for it to read a stable value, it will read then the exact piece, so preventing a player from making it change rapidly as you're lifting it up and down.
Here's a prototype version of our design for the battery system. The system is rechargeable through USB-C design with a 9-volt input that goes to the batteries, and finally to a voltage regulator that will be powering the rest of our systems that we showed earlier. Just to show, we can measure the voltage on the output of the voltage regulators to show that it gives us an average input of 5 volts that we'll be using for our project. Now it's time we talk about the engineering specifications of our chessboard, but most importantly, showcase some of the key specifications that we deem to be the most important for successful final design. The specifications you can see in the table are great guidelines to keep in mind during the design of our projects, spanning both senior design semesters. These criteria served as a baseline to establish some constraints that needed to be satisfied, but our group aimed not only to meet said criteria, but also to surpass them when possible. In the following segment, we'll be showcasing our detection system's response, the accuracy of our system when detecting said pieces, and its capability of differentiating each piece based on our sensor reads. For this test, we'll have Nikolai place a piece on the detection system and measure the time it takes for the program to display the detected piece. We can see that with a time of only 0.35 seconds of delay, we are confident that the board will allow for the fluid gameplay that we wanted from the beginning.
Go.
Here, I'm going to demonstrate another key specification of our project, the piece identification accuracy. I have a queen filter placed here. Placing it on top shows the queen, can move it away, and it will show it's a queen again. I can also do this with another filter or even a lack of filter to show off the king. Moving it off, place again, and it's a king. And through our various testing, we have reached about a 95% accuracy, which is our minimum, with this very temporary setup using tape that's very adjusted. So we definitely expect to surpass that number when we implement into a much more stable final design.
So for our third key specification of our project, we are demonstrating that we have 7 different piece values, and we are showing this through the use of various filters. We have various light intensity reducing filters, ranging from ND4, ND8, ND2, ND16, ND6, blackout stickers, and all of these filters will be put at the bottom of the bases that will allow us to get a certain range of values to identify what piece was just lifted by the player.